today's topic is ozonolysis, which is the continuation of the chapter 2, that is the even reaction. So let us see ozonolysis. In ozonolysis, alkenes oxidize with ozone to form the ozonites, and which are the unstable compounds. Okay, so when it reduces with the zinc and water, it gives the aldehyde and ketones. The reaction is called as ozonolysis. For example, the ethene reacts with the ozone, that is O3, it gives the ozonite, and in the presence of the zinc and water it gives the aldehydes only. Okay, that is the formaldehyde, and this one also the formaldehyde. Okay, so it is clear that if the carbon forming the double bond, it carries the hydrogen atoms attached to it, it gives only the aldehydes, and otherwise it gives the ketones. Okay, so for example, 2-methyl 2-butene, when reacts with the ozone, it gives this ozonite compound, and in the presence of zinc and water it gives the acetone and acetaldehyde. It means that when this carbon carries the alkyl groups, both alkyl groups, then the acetone is formed, otherwise aldehydes are formed. Okay, next, mechanism of ozonolysis of alkene. So first step involves nucleophilic carbon-carbon double bond attacks the positive charge of ozone, while the second nucleophilic attack by the negative charge of the ozone oxygen atom of the ozone takes place at the other end of the carbon-carbon double bond, and thus there is a formation of monoozonite. Okay, next step is the cyclic monoozonite that rearranges itself to ozonite. Okay, so there is a product which is formed in the first step, that is monazite. This rearranges itself to the ozonite. Okay, next step is the decomposition of the ozonite after the reductive workup, resulting into two carbonyl groups. Okay, so ozonite which is formed in the second step, that is reduces itself to the two molecules of ketones. Okay, understood? Next, application of ozonolysis. So the process of ozonolysis is used to locate the position of double bond in an alkyl molecule. Okay, so the double bond is obtained by joining the carbon atoms of two carbonyl compound. Let us see the product of ozonolysis of two molecules of acetaldehyde. When two molecules of acetaldehyde combines, that gives the but2ene. Okay, so this is the two molecules of acetaldehyde. When combined, there is a joining of carbon atoms of two carbonyl compounds, and there is a formation of but2ene. Next example is two molecules of the one of the acetaldehyde and second is the acetone, that is the propanone ketone, and this gives the 2-methyl but2ene, and there is a combination of the two carbon atoms of two carbonyl compound. Okay, so it is noted that the ozonolysis helps in locating the position of double bond. Okay, understood? Next, electrophilic addition reaction. Then what is electrophilic addition reaction? It is a reaction in which a substrate is initially attacked by an electrophile, and the overall result is the addition of one or more relatively simple molecules across a multiple bond. So let us see the mechanism of electrophilic addition reaction. In the first stage, the charge which is present on the electrophile is attracted towards the electron density of the double bond, and as the electrophile approaches the double bond, the pi bond breaks, and one of the atom of electrophile that bonds to the carbon atom, forming the carbocation, that is the positively charged carbon atom, and leaving its other atom with its lone pair of electron. Other step is, in the second step, the atom with its lone pair of electron, that is acts as a nucleophile and attacks the carbocation causing the atom that is bonds to it, that is this electrophile nucleophile that bonds to the second carbon atom, and this is the electrophile which is added in the first step. Okay, so this is the mechanism of electrophilic addition reaction. Okay, understood? Next, examples of electrophilic addition reactions. Halogens, particularly chlorine and bromine, react with alkene in the presence of an inert solvent, that is carbon tetrachloride, to form dihalogen derivatives. So let us see the mechanism of addition of bromine to alkenes. For example, ethene. Okay, so in the first step, that is the bromine molecule, which is a non-polar. Why? Because its electron pair between the two bromine atoms is equally shared between the two atoms. As the bromine molecule approaches the ethene molecule, that is the electron cloud of the carbon-carbon double bond, that gets repelled, okay, disturbed, and as a result the electrons of the bromine molecule that get displaced away from the bromine atom nearer to the ethene molecule. Okay, and therefore the bromine atom which is near to the ethene molecule gets positive charge and other atom gets negative charge. Okay, so this positively charged bromine atom that attacks the pi electrons of the double bond, okay, and giving the carbocation, that is the positively charged carbon, and a negative charged bromide ion. Okay, so this negative charged bromide ion then gets added to the positively charged carbon atom, and there is a formation of the addition product. Okay, understood? When the alkene is unsymmetrical, then two products are possible. For example, when propene is treated with the HBr, both 2-bromopropane and 1-bromopropane are formed. So, in these cases, the addition is governed by the Markovnikov's rule proposed by the Russian chemist Markovnikov, which states that during the addition of the HX and water to an alkene, the hydrogen atom will add to the carbon of the double bond that already have the greater number of hydrogen atoms. Let us see the mechanism of addition of the HBr to unsymmetrical alkene. Okay, so consider the attack of electrophile on propane molecule. The two intermediate carbocations are possible. That is, this is the secondary carbocation and this is the primary carbocation. We know that the secondary carbocation is more stable than the primary carbocation. Therefore, the attack of H plus ion on propene results in the formation of more stable carbocation. This ion further reacts with Br bromide ion to form the addition product. Okay, understood? Next, peroxide effect. Kharash and Mayo observed that when HBr is added to an unsymmetrical double bond in the presence of organic peroxide, example benzoyl peroxide, the reaction takes place opposite to the Markovnikov's rule. This is known as the anti-Markovnikov's rule or peroxide effect or Kharash effect. According to anti-Markovnikov's rule, the addition of HBr to an unsymmetrical alkene, the bromide atom will join to the carbon carrying more hydrogen atoms, while hydrogen atom will go to the other carbon atom. For example, HBr when added to the propene in the presence of the peroxide, there is a formation of 1-bromopropane, that is the major product. Next, let us see the mechanism of addition of HBr in the presence of peroxide occurs by free radical mechanism. Okay, so first two steps results into generation of free radical, that is the bromide ion. Okay, then it adds to the double bond in such a way that it gives rise to more stable free radical. Then this free radical then abstracts the hydrogen atom, that is from the HBr, to complete the addition product. This is the addition product. Okay. Then it is noted that peroxide effect is applicable only to HBr, not to the HF, HCl or HI, because with HBr the reaction is exothermic and hence free radical mechanism is possible. With HF or HCl, the attack of these do not follow free radical mechanism because attack of carbon radical with HF or HCl is endothermic. Thus, peroxide effect is observed only in case of HBr. Okay, understood? Okay, thank you. Then we will see in next video the stability of conjugated dienes. Okay.